Welcome to another episode of learning. Please like my videos and share them with your friends and colleagues. Please join as a member in my channel and support me and my channel. Please subscribe my channel if you have not already subscribed. Thank you. Yes, we continue the discussion of the solutions of the problems that have appeared in the CSIR National Eligibility Test held in the month of March 2025. It is a rescheduled examination for Assam Center. In this video, we discuss the solution of a problem from the section analysis, and it is related to the concept of bijection between two sets. This question is placed in part B, which is a multiple choice question, and it carries 3 marks. The question ID is 706501. This question is suitable for all these examinations. Right. The given question is, let A, B be two non-empty subsets of R. Let S be the set of all continuous real valued functions defined on A. Capital T is the set of all continuous real valued functions defined on B. U be the set of all continuous real valued functions defined on A cross A, the Cartesian product of A with itself. Which of the following statements is true? We are given 4 options. Option 1, if A is finite, then there exists a bijection between S and U. Option 2, if A is finite and B is equal to the closed interval 0, 1, then there is no bijection between S and T. Option 3, there is no bijection between S and U for any choice of A. Option 4, if A not equal to B, then there is no bijection between T and U. Let's now discuss the solution of the problem in detail. We recall the following concepts and the results. Let capital X and capital Y be any two non-empty sets. A bijection between X and Y is a bijective map or a bijective function phi from X to Y. Bijection means a bijective function. A result, a bijection exists between two sets X and Y if and only if they have the same cardinality, that is the cardinality of X is equal to cardinality of Y. Another result, every real valued function defined on a finite set is always continuous. Every real valued function defined on a finite set is continuous. Right. Let us take the option 1. If A is finite, then there exists a bijection between S and U. S is here, U is here. Okay. So let A be a finite set. Let the cardinality of A be N. Now S is the set of all functions f from A to R. F is continuous. Just now we have seen every real valued function defined on a finite set is continuous. Therefore, this set is precisely equal to the set of all functions f from A to R, where A is finite. Where A is finite, every function, every real valued function defined on A is continuous. Therefore, they will have precisely the same sets. Now, what will be the cardinality of S? Cardinality of S from here, cardinality of R to the power of cardinality of A. Yes, this is what we have learnt in our intermediate. That is equal to cardinality of R is continuum C to the power of cardinality of A is N. C power N, C into C into C is C. This is the arithmetic in continuum. And since N is a natural number and a finite one, N is a finite natural number, therefore C power N is C. Right. Now what about U? U is the set of all f from A cross A to R. F is continuous. What is A? Finite. A cross A is finite. Therefore, this is precisely equal to the set of all functions f from A cross A to R, because A is finite. I'm sorry. Right. Now what will be the cardinality of U? Cardinality of U is cardinality of R to the power of cardinality of A cross A. Cardinality of A is N. Cardinality of A cross A is N cross N. That is C power N square. N is finite, N square is finite. Therefore, C to the power of N square is C into C into C. N square times N square is finite, and that will be C. That is continuum. So, what did we see? Cardinality of S is C. Cardinality of U is C. They have the same cardinality. Therefore, there is a bijection. Thus, cardinality of S is equal to cardinality of U. Therefore, there exists a bijection between S and U. We have seen, that is the result what we have recalled. Thus, option 1 is true. Let us call on option 3. There is no bijection between S and U for any choice of A. No, this is not true. For the choice of A, when A is finite, we have seen that there is a bijection between S and U. Right? So, when A is finite set, by option 1, option 1 is true. By option 1, there exists a bijection between S and U. Therefore, this option 3 is not true in general. Let's move to the next slide. Right. Option 2. If A is finite and B is the closed interval, unit interval 0 to 1, there is no bijection between S and T. A good result. Now let us see. Let A be finite. Then cardinality of S is C. Cardinality of S is C when A is finite. Correct. Now we have T is a set of all continuous real valued functions defined on B is equal to the unit interval 0 to 1. This is precisely C01, what we have studied in our MSc classes. This is C01, continuous real valued functions defined on the closed interval 0 to 1. Right. Now, here you must know this result. Whether you know this result or not, I do not know. If you know it, you take it for granted. If you do not know it, I will show you how this result is true at the end of these options. So what is that we have? C01 is contained in the set of all functions, real valued functions defined on the rational numbers in the interval 0 to 1, Q intersection 0 to 1 to R. C01 is embedded in this. This is the result, what I am going to use. Therefore, T is C01 is contained in this one, the set of all F from Q intersection 01 to R. Now, the cardinality of T is less than or equal to the cardinality of this. What is the cardinality of this? Cardinality of R to the power of cardinality of the domain Q intersection 0 to the closed interval 0 to 1. That is, cardinality of R is a C. The cardinality of Q intersection 0 to 1, there will be infinitely many rational numbers in 0 to 1. It is an infinite set of rational numbers. It is an infinite subset of rational numbers. Where rational numbers is countable, therefore this infinite set is also countable. When it is countable, its cardinality is LF0. So C power LF0. What is C? We know 2 to the power of LF0. To the power of LF0. That will be 2 to the power of LF0 multiplied by LF0. That is LF0 only. 2 to the power of LF0 is C. Right. This is cardinality of T less than or equal to C. Right. But now consider T prime is the set of all functions 0 to 1 to R such that f of x is equal to k, k belongs to R. So T prime consists of what? Constant functions. Every constant function is continuous. Therefore, T prime is contained in T. So clearly, T prime is contained in T. And what is T prime or the cardinality of T prime? The cardinality of T prime is the cardinality of the set of all those k, k belongs to R, that is precisely cardinality of R. So cardinality of T prime is equal to cardinality of R is equal to C. Right. Now, and we have T prime is contained in T. T prime is contained in T. Therefore, cardinality of T prime is contained in cardinality of T. Therefore, C is contained in cardinality of T. But we have seen cardinality of T is C is less than or equal to, not contained in, C is less than cardinality of T. And but we have seen cardinality of T is less than or equal to C. So combining these two things, C less than or equal to cardinality of T and cardinality of T is less than or equal to C. Therefore, cardinality of T is equal to C. Thus, S and T has the same cardinality C. Therefore, there is a bijection between them. Thus, there is a bijection between S and T when A is finite and B is the closed interval 0 to 1, since they have the same cardinality C. But it is given in option 2, there is no bijection between S and T. Therefore, option 2 is not true. Now, call on option 4. If A not equal to B, then there is no bijection between T and U. Let's see. Now what we see is, let A be finite and B be 0 to 1. A is finite set, B is an infinite set, therefore A not equal to B. But we have seen when A is finite, cardinality of U is C. And when B is 0 to 1, the cardinality of T, just now we have seen, it is C. It is C. So they have the same cardinality, therefore there is a bijection. So there is a bijection between T and U. When in the case of A is finite and B is 0 to closed interval 0 to 1, when A not equal to B, there is a bijection. So option 4 is not true in general. For these particular choices, this is the case. So summarizing all the options, the answer to this question is option 1. That is the detailed discussion of the solution of this problem from the section analysis, which is related to the concept of bijection between sets. Agreed. Agreed. Now, for those of you who do not know this result, that is C01 is embedded in the set of all F from Q intersection 0 to 1, closed interval 0 to 1 to R. If you do not know, continue seeing the video. If you know it, if you want to quit, you can quit here itself. So, we will now go to the next slide for the proof of C01 is contained in the set of all F from Q intersection 0 to 1 to R. This is the result. We first prove that a continuous real valued function on the interval 0 to 1 is determined by its values on the dense subset of rational numbers in the closed interval 0 to 1. We want to prove that a continuous real valued function on the interval 0 to 1 is determined by its values on the dense subset of rational numbers in 0 to 1. Let F from 0 to 1 to R be any continuous function. Then its values, because it is defined on 0 to 1, F of Q, we know for every Q belongs to Q intersection 0 to 1. Yes. Let alpha be any irrational number. Right. Since Q is dense in R, there exists a sequence Qn, n greater than or equal to 1 of rational numbers in 0 to 1 that converges to alpha. Correct. That is, limit n tends to infinity of Qn is alpha. Right. What is F? F is continuous on the whole of 0 to 1. What is alpha? Alpha is an element of 0 to 1. Therefore, F is also continuous on alpha. Now, F is continuous at alpha since F is continuous on the whole of 0 to 1 and alpha is a member of that. Now, by sequential continuity, limit n tends to infinity of Qn is equal to alpha will imply limit n tends to infinity of F of Qn is F of alpha. F of alpha. So, the same function F, what we know, its action on any irrational number is known. So, this shows that F is completely determined by its values on the dense subset of rational numbers in 0 to 1. Right. So for each function in C01, you can find an element here. We continue that. We claim this result and define a map phi from C01 to the set of all f functions from q intersection 0 to 1 to r by phi of g, g belongs to C01, is the restriction of g on the set q intersection 0 to 1. For every continuous function, we take its restriction in this set. So, we want to prove that phi is 1, 1. Phi is 1, 1. So, let us take GH be two elements in C01. Phi of G is equal to phi of H. Means what? G of Q is equal to H of Q for all Q belongs to Q intersection 0 to 1. Yes. Yes. Since Q intersection 0 to 1 is dense in 0 to 1, for any x belongs to 0 to 1, for any real number belongs to 0 to 1, there exists a sequence of rational numbers Qn n greater than or equal to 1 in Q intersection 0 to 1 such that Qn converges to x as n tends to infinity. By continuity of G and H, we use the sequential continuity concept here. G of x is equal to limit n tends to infinity of G of Qn and limit n tends to infinity of H of Qn is equal to H of x because G and H are continuous. And these two are equal because G of Q is equal to H of Q for all Q belongs to G intersection closed interval 0 to 1 because phi of G is equal to phi of H. So, these two are equal. So, thus they are all equal. Thus, G of x is equal to H of x for whom? For all x belongs to 0 to 1. Then G and H are precisely the same functions. Thus, we get phi is 1, 1. When phi is 1, 1, C01 is entirely contained in the set of all f intersection f which are the real valued functions defined on Q intersection 0 to 1. This is contained in since phi is 1, 1. That's the result. That result I have used in the previous result, right? So, I am sure that you have understood this result, and this result has been used earlier in some discussion, right? I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please join as a member in my channel and support me and my channel. Please subscribe my channel if you have not already subscribed. Yes, I am sure we will be meeting once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.